Okay, so welcome to the final workshop of beginner track this quarter. Really glad you guys managed to stick it through all the way to the end. So last week we sent out the linear regression portion of the guided projects on Discord. So hopefully you guys had a chance to take a stab at it. So we're gonna go over the solution to the linear regression part of the guided projects at the beginning of this workshop, and then we are going to let you guys work on the logistic regression portion of the guided projects for the remainder of this workshop pretty much. All right, so let's get started. So I guess for you guys who have looked at the notebook, so first we're just doing like a sanity check where we're just learning this really simple function, which is a line. We're also adding some noise using the normal distribution implemented in NumPy. So f of x here is just this line here, pi x plus 10, and then we have another term, which is the noise distribution that we're adding to the function that we're learning. And then we're using numpy.a range to generate 100 data from 0 to 100 for x. And then our y are generated with the f of noise function that we implemented. So if we want to plot this out, we get a nice, pretty linear distribution here. So our model should do pretty well to learn this function. So here we're doing some more pre-processing, and then we're using train test split from scikit-learn to split our data into train split and test split. So hopefully you guys are familiar with this function. I think we've covered this. We've gone over this like several times in our previous workshops. So if there's any questions on this, I'm happy to answer them in chat. Otherwise, I'm going to move on. So another thing that you guys should be familiar with is how to implement like classes in Python. So if not, here's like a simple example that you guys can go through yourselves. But basically the main idea is when you create like a object of a class, in this case rectangle, you call the init function. So here, like I'm creating like a rectangle with base of 3 and height of 5. So I'm invoking this init function, also sometimes called like a constructor. And then you can also invoke methods on the rectangle object that I created like here. So you can invoke like a method of a class using this dot notation with the parentheses. So yeah, the reason why we're covering class here is because our linear regression model is implemented as a class, which is also the case in the actual scikit-learn library. So actually the API for our linear regression class and the API in the scikit-learn library are like really similar, and it's intended that way just to show you guys we can actually like implement something that is in production quality just from what we've learned, just from what we learned in this track. So that's pretty cool. So yeah, here we provided like a brief review of linear regression. We have our MSE loss here, and also the gradients DLDW and DLDB. So note that these gradients are in matrix form, because this is also how we would implement it in NumPy. And we also have the gradient descent update rules here. So hopefully this should all be reviewed. So I think the main, I guess the meat of this guided project is really in this linear regression class. So the first method that you guys hopefully implemented is the predict method. So basically, we want to make a prediction using the linear regression hypothesis. So hopefully you guys had a chance to take a stab at this. But basically, we want to take the matrix products between our data, which is X, and also our weights. And then we add a bias term to it. So this would give us our predictions. Okay. And then the next method in our linear regression class is the loss, which is our MSE loss up here. So using one of our universal function in NumPy, which is the average function, we can, so first we compute like the difference between y and y hat, which is the ground truth and the predictions. And then we square it. And then we take like basically the average of all the square differences. So that gives us our MSE loss. And then the next part here is comparing the gradients of our loss. So we actually provided like these two really nice equations. So you guys can literally just translate this into NumPy and should be good to go. But in case you're wondering, this is how you would implement these two equations in NumPy. So we have like X transpose matrix multiplied with y hat minus y, and also NumPy.sum y hat minus y. So that's exactly what we have up here. And then the last method in our class is the fit method. So in the fit method, we're fitting the model using a training data and the target. So we have this training loop here, which basically run for like the number of epochs that we have. So first we make a prediction using the predict method that we implemented. And then we compute the loss using the ground truth and the predictions that we made. And then we compute the gradients using self.grad, which is the grad method up here. And then we perform the gradient descent update using these update rules. So we have self.weights minus equals self.alpha, which is the learning rate, times dw, and self.bias minus equals self.alpha times db. All right, so let's run this cell. And then let's try fitting our model to the training data that we have up here, which looks something like this. So our linear regression model should be able to do pretty well in theory. And of course, I ran them out of order. Okay, so this is what our loss looks like. So our loss function is decreasing over time, which is what we expect. And then we can also like print out the weights and the bias. So this is actually pretty close to the function that we're trying to learn, which is, I believe, pi plus 10. Or at least the weight is pretty close. The bias is a little bit, is not very close to 10. So we can try plotting out the results. So yeah, this is what the function or the linear regression model predicts. So as you can see, it's doing pretty well on the training data and then slightly worse on the test data, which is expected. And then we also, in the next part, we also explore like the effect of like using different learning rates. So I think using, so the blue line is the smallest learning rate. So the loss like decreased like pretty slowly. And then we have the orange line, which is like the learning rate in between. So it's decreasing slightly faster than the blue line, but it's still not as fast as like the green line, which has the highest learning rate. So in this case, I guess picking the highest learning rate would make the loss decrease like the most quickly. But I guess if you pick a learning rate that is too large, the loss might not actually like converge. It might oscillate or even diverge if your learning rate is like extremely large. So just keep that in mind when you train your models. So the next part of the linear regression guided project is pretty cool because we actually apply our model to real world data sets. So this data set is from scikit-learn. It's the Boston housing prices data set. So I think we can just ignore this warning. And then if you're interested, you can look at the documentations. So these are all the features in our Boston housing data sets. Some of them are pretty interesting. So yeah, let's split our data again using train test split, and then fit our linear regression model on the data set. So this is gonna take a little bit. I think it will finish like within a minute, but also feel free to like tweak the learning rates and like see what kind of results you get. Okay, so let's see what we have. So the R2 score here is around 0.61, which is reasonable. You can also compare like our results to how well the actual model in scikit-learn performs. So the scikit-learn model has a slightly better R2 score, which is expected because I'm pretty sure the scikit-learn model uses the closed form solution, which is guaranteed to like find the optimal solution for linear regression. So yeah, this is basically like the best you could perform on this data set, and we're not too far away from it. So yeah, so great job. Hopefully you guys are following with the Gaia projects. If you guys have any questions, I'm happy to take them now. If not, I'm gonna hand it over to Claire, who's gonna go over today's portion of the Gaia projects.
All right, let me share my screen really quickly. All right, do you see my screen?
Yeah, you're good to go.
All right. So hello, I'll be going over the logistic regression part of this workshop. You'll notice that it does look quite similar to the linear regression part. So we'll get to what's different in a little bit. So as before, we're going to start by importing all the modules that we're going to use for our workshop today. And then we'll set our random seed like we did last time. Now we're going to create some more random data, and now we're going to set it with a different shape. So as you might notice, we have two different kinds of data here. We have our x1, x2. So with the scatter plot, if we run that really quick, then we should have something that looks kind of like this with our two different classes. Now, if you can gather from our combining here with our x1, x0, and x1, we have an x of 200 by 2, and our y is just 200. So now we can split our data into our testing and training like we did last time with scikit. So let's run that really quickly. Now, another refresher, I suppose, about how classes work in Python is that you have your class as usual. Now we have our initializer, and then we have a couple functions. So if we run this, and if we're trying to calculate the area and the perimeter by passing in some values, then you will be able to pass some values in like this and calculate your area and perimeter. So that's just the basic overview of what we also learned with linear regression. It also applies to logistic regression, so that's why I thought I'd go over it again. Now, let's go into a slight review of logistic regression. So you might have seen these in our previous workshop slides, but we have our hypothesis, again, with our weights and biases. And then we have our loss function with binary cross entropy. And now we can use that loss function with our weights and biases to get our gradients, to get our new weights and biases with each gradient. So that's the basic equations of logistic regression. And now we get into the part of the workshop that you guys get to work on. So right here, we have some functions set up for you in a class, very similar to the linear regression workshop. And we'll give you some time to work on it. You'll know when to do things when you see a to-do comment like this. So we will give you, 15 to 30 minutes to work on this by yourself. You should be able to find a skeleton to this in the feedback form, along with the solutions for the linear regression workshop, which should help you in this logistic regression workshop. So let me know if you have any questions, and if not, then happy coding.
Yeah, let's take 30 minutes to work on the logistic part of the, I guess, class. If you guys have any questions, feel free to unmute or type in chat. We're happy to take them.
I have a quick question.
Yeah.
For sure.
So I'm not like very well versed in Python, but are the pass statements like necessary?
Oh, those are
Or
just
what are they for?
placeholders. You should
Oh, so
remove
so I
them.
can
Oh
just
yeah,
remove them?
that's where you would.
Yeah, you should remove them
Okay.
when you like implement your
Okay, because
model.
when I tried it with the like linear regression one, I left it in there and it seemed to work.
Yeah, I think it's not gonna like break your code, but it basically just does nothing.
Okay,
Or
cool.
makes your code do nothing. Yeah.
Oh, by the way, Claire, can I ask you a question?
Yes, hello?
Yeah, can you hear me?
Yes, I can.
Yeah, so the thing you just posted in the Discord, it's the part 1, right?
Yes, so you can find the part 2 in the feedback form. I don't know if it's been shared to the chat after you came. So I'll share it again if you give me a second.
Oh yeah, it's there. Guided project 2 skeleton. Yeah, right there.
All right, I posted again. Hopefully we can get both the answers to part 1 and then the skeleton for this one should also be in there.
Thank you.
You guys have 20 more minutes, by the way.
Oh, and by the way, did you say you upload the project 2 link in the Discord? Because I can't really see it.
It should be, if you click on the link I sent in the chat, that
Yeah.
should take you to the feedback form, and that should
Yeah.
have the skeleton. It won't be in the
Right.
Discord.
Okay, yeah, and the guided project 2 is there, and yeah, okay.
Got it?
Still loading. Oh, there you go. Okay. And the guided project 2's feedback form, there's a solution for that as well, right? Or oh no.
Oh,
Yeah,
we'll
we'll
be
post
going
the
over the
solution
solution.
after. Yeah,
Oh,
we'll
okay.
go over a solution.
We'll be
as
going
well.
over it.
All right.
I have a quick question.
Yeah.
So that like the line right below where all the stuff's like implemented, where you're calling the logistic regression function, should the x train parameter be with like a lower x, lowercase
Yes.
x?
It should.
Okay.
And that happens actually again later, I think. So just switch it. Yeah, it happens in the which accuracy do you expect to be higher section. So you can just switch all of those to lowercase x's and then it should work.
Okay.
All
Okay.
right. Thank you for bringing that up. You guys have about 10 minutes left. If you have any questions, feel free to put in the chat or unmute.
Honestly, you guys can take like as much time as you guys need. If you guys are done, please let us know so that we're not just like waiting here. But yeah, definitely don't feel stressed about time.
Oh, one quick question about the class. So for the linear regression class that we're implementing, so the bias, it just says like float, right? So is it like, I don't know, like what kind of float should it have? Because like, like is 0.0 or like 1.1?
You should be in the logistic regression class. Are you in the logistic regression class?
In the library? Oh wait, so sorry, could you repeat that again? I didn't quite hear.
Oh, you said you were in the linear regression class.
Yeah,
Is that right?
yeah.
We're actually going over logistic regression right now.
I'm pretty sure it's just like a float. I don't think there's any like dimensions to it. It's just a scalar.
Oh, just any number is fine.
It should be. I'm pretty sure it's gonna. So the bias should be determined by like the learning itself. So like as you train your model, the bias is going to like fit to the y-intercept.
Oh, okay.
But like obviously in this case, I don't think it's doing a very good job. Because like in the notebook that I ran, the bias at the end was like 0.65. But like the actual y-intercept is 10. So like I think it's just because of the noise in the data.
Oh, okay.
But yeah, just a hint. I think most of the logistic regression should be really similar to the linear regression implementation. So if you guys are stuck, definitely feel free to check that out as like a hint.
Oh, by the way, is the learning rate the slope of the graph of the linear regression? Because that's basically A, right? And bias is the y-intercept, as you just mentioned before.
So the slope of the graph should be the weight, yes.
Should be the learning rate, right? The LR.
Oh, the learning rate is like a hyperparameter.
Oh.
So in theory, it could be like anything that is like within a reasonable range, and the model should be able to learn. If it's too small, then it will just take forever to converge to minimum. if it's
Yeah.
too large, it could diverge or just oscillate without converging.
Yeah.
But usually the learning rate is determined like empirically.
Oh, okay. Then
So like there's a part where we're like basically experimenting with like a bunch of different learning rates and see how fast the loss decreases.
yeah.
Does that answer your question?
Yeah, so we're basically testing a lot of learning rates, but so that's A, right? So, and since y hat equals ax plus b, now if we make a prediction, then we basically have to use the learning rate inside the object, right? So that's self dot lr,
Wait,
Right.
which part are you talking about?
like define predict that part,
Predict.
because we have to make a prediction
think-
and yeah,
we're multiplying x with self dot weight. So that's the weight of the model.
Oh.
The learning rate should be a float. The weight should be a vector.
oh,
The learning rate is only used in the gradient descent update rules.
oh, okay. So wait, so sorry, kind of confused right now. So for the data, right? So it's n by f, right? So basically the number of
Yes.
samples and number of features,
Uh-huh.
and y equals and labels and slash targets, but it only has the number of samples. It doesn't have the number of features, right?
So in NumPy, usually like if the second dimension is like a 1, it's usually just omitted this way.
Yeah.
So it's just
Oh.
like each label is just a number. So it's basically like an n by 1 column vector. But
Oh,
like the
right.
second dimension is like omitted.
Yeah.
Same holds for like the weight. So the shape is like the number of features. So f comma nothing.
Right, right.
Does anybody feel like they need more time? You can unmute or just put it in the chat. Because if not, then we will start going over the answers. So I'll give you a couple seconds, and if everyone's good to go, then let's get started. All right, then let's get started then. So we have a very similar initialization function to linear regression, where we're basically just setting up all our variables. Now, this has already been done for you. You can see we're setting our weights and biases just random for now. Now, for the first part, for the activation function, we can use the sigmoid activation function and just call it division 1/1 plus e to the -z. That should be it. And then we can just return division. Oh, that should be it for this block. We're just putting in the sigmoid activation function. Now, similarly, for the predictions function, it is also just one line of code. So we have our prediction, and then we will do a dot product. And then we'll add the bias. And then we will just return our predictions. Which we are using our activation function for. So on to the next step for the loss. We can just use our binary cost entropy function that we went over just slightly earlier. And use NumPy average function. And then we can add in our y hat. Sorry about that. Almost done. And then so in theory, we have just put in our binary cost entropy equation. And now we can just return log loss. So that is our loss function.
Just one second. So we're doing that because we're using the logistic regression, right? The np.log and like np absolute stuff like that.
Yeah.
Because yeah.
So it should be pretty similar to this function that we have up here, where we take the average of the log losses. So you can refer to our equations up here.
Oh, okay.
Just to add to what Claire said, so np.log and np.absolute, those are like what we call universal functions in NumPy. So you can pass in like a NumPy array, like y hat, and then it'll apply that function to every element in your NumPy array. And it's much faster than using a for loop.
Definitely. Does that answer your question, Mark?
Yeah.
All right, cool. So now we have our gradients. These might look pretty similar to linear regression as well, but we have our weights step, I guess, and then we can use again our equation of the transpose and y hat minus y. And then for the biases, it looks pretty similar. We will sum up y what did I do? Y hat minus Y. Let me quickly. All right. So now we have these and we can just return them. Now, this might be the hardest part or the most involved part, I guess. We will now fit the model to our training data. So let's start off with our predictions. With the function we just made. And then we can use our loss with the predictions. And then we will set our weights and biases. And now we'll do our steps, which you might remember from the gradient descent slides. So we'll use our gradients that we calculated here to update our weights and biases. All right, and then we just append the loss that we calculated to our loss array. So this is just to plot the figure. So if we run this, hopefully everything's all right. Now, as Gabriel, I believe, pointed out earlier, this should actually be a lowercase x to match with our x train from all the way up at the top. So if we run this, hopefully without any problems, we now have a graph. And in addition, we can also visualize, or we can just print what our weights and biases are right here. So we have our two weights here, and then we have our bias, which I suppose you can't really tell from this graph. So yeah. Now, to visualize it further, at the beginning of this workshop, you might remember that we have a graph something like this with our x1, x2, and we came up with this scatter plot. So now let's look at what our model looks like, and hopefully it looks pretty similar. If you just run this block really quick, you get a similar looking graph, but it might be pretty hard to visualize the differences. So what we can do is we can actually show the decision boundary, which, if you remember, is the boundary that has been determined to at least be the best fitting boundary between the two classes. So if we run this, we can see our decision boundary. Quite a bit of orange on the left side, but I suppose that's okay. So some food for thought is, oh, once again, these should be lowercase. Which accuracy, the training or testing data, do you guys think will be higher? You might have run it already, but feel free to put it in chat if you feel like it. Training, yeah, because that's what we use to train our data. So if we run this really quick, we'll see that our training accuracy, pretty good, 93. Test accuracy is slightly lower at 87%. So I believe that's about it for this workshop. In case you're interested, another thing, you can continue with this after beginner track, but it's recommended that you finish advanced track first, is projects. So if you're interested in finding out more about that, then we have some links down here for you. And I believe with that, I will be turning it back over to Jensen.
All right, can you all see my screen?
Yep.
Yep.
All right. So congrats for making it this far into all the way to the end of our beginner track, and thank you for sticking all the way to the end. We really appreciate it. So we actually cover like a lot of material this quarter, and you guys should be really proud of all the effort that you guys have put in. So if you guys are wondering like what comes next, so all the stuff that we cover in beginner track is what's known as the domain of shallow learning. This I guess compared to like deep learning, it's so the model in shallow learning are a lot simpler with like, if you're familiar with like neural networks, they're like more layers. So that's where the deep learning comes in. So we encourage you to like explore other concepts in the shallow learning domain, such as lasso regression, rich regression, PCA, LDA, and other cool stuff. Sometimes they even work better than deep learning, depending on your application. I guess a good library for shallow learning is scikit-learn. We already like cover some of the models in scikit-learn, but feel free to check out other models. Alternatively, if you're interested to explore deep learning more, we'll also offer advanced track, in which we'll cover like, I guess, some of the models in deep learning. I believe advanced track should be offered next quarter, and definitely fall quarter next year. So other resources that you guys might find helpful. So first of all, Medium is your friend. There are so many like cool AI blogs and articles on Medium. There's usually like something really cool like every week. So in my free time, I usually just go to Medium and like read like maybe an article or two about like an AI topic. And another thing is the AI Weekly, which is my personal favorite AI newsletter. So you can get caught up with all the cool like weekly AI news. And I guess not last but not least, we also offer advanced track and projects. So those would be the more natural next steps for you guys to follow up on your interest in AI and ML. So yeah, that's all from us this quarter. And thank you so much for coming to the final workshops. This is our feedback form. If you guys have any feedback for us, definitely fill this out. It's anonymous and it'll help us improve our workshops. And also please stay connected through our Facebook group here. So yeah, thanks for coming.
I have just one quick question. So
Go for
I
it.
think the recordings from workshop 1 to 5 are posted, but for the 6th one where we deal with like NumPy and Pandas, like I can't like see the link. So like, where can I see it? Is it like still being processed?
Let me double check. I believe it's still being processed. I personally like upload the recording to Drive already, but like I believe we're still processing it. So we'll probably like post it like either tonight or tomorrow. And also we're also gonna post like the recording of this workshop like soonish.
It
Right.
might be in the cluster, the NumPy and Pandas.
Is it?
Oh, the recording CBA. No, it's